So is it visible?
No, madam, it didn't come. Just try to do one more time. Yes.
Is it now?
No, 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 no. It's not coming.
Okay, okay, just wait a minute. Okay. Yes. So it should come now.
Yeah, it is coming now. Yeah, it is coming.
Okay. Hmm.
Yeah, it is coming. It's on the way now. Yeah, yeah, yeah.
Okay.
Okay, madam. So now we can start.
Yeah.
Professor Chattopadhyay is from, she is associate professor in the discipline of physics, IIT Indore. So, madam, I am requesting to present yours lectures.
Hmm. Okay, thank you, Srimanta, and thanks to all of you for joining us at IIT Indore. So, good afternoon. And just I am going to start my lecture today on materials engineering for energy research. So, as you know, that is the course coordinated by Dr. Sumanta Prakira on advanced technology for materials physics and engineering at IIT Indore. So within that, this lecture is going to be, presented today. So first, just I wanted to quickly give a impression about the location of Indore. All of you know since you are from India, so that is because it's a good location at the center of India, and it has been established in 2009, and kind of 11 years now. So it is completely grown up now, the institute, and already coordinator and dean of academics in the morning has given a brief description about our institute, that we are now with a high ranking and this thing. So all of you are most welcome to visit us at some point if you are interested to interact the faculty members and like that, and also research opportunities. And now I'm going to tell you about just very quickly about my research focus, so that I can connect my presentation with my focus. So basically that I used to work on the interface effect in in energy research, that is kind of graphene, 2D materials. So second, soft matter, and then of course X-ray scattering is a important tool for many of my research area. That kind of X-ray scattering means not only the XRD, which is very commonly known, but X-ray reflectivity, GSAX, which is grazing incident, small angle X-ray scattering, grazing incidence diffraction, because all these things are very important, and many important information you can extract for this kind of techniques. So if I get chance related to my lecture, I will give some glimpse of this techniques as well. So, and of course, electrical energy storage, or sometimes people used to say even electrochemical energy storage, which is batteries or supercapacitor. But mostly I am focused on the building better batteries. So aluminum ion batteries, lithium ion batteries, like that. So it is metal ion batteries to make the material or to prepare the system for the better performance. Okay, so this is of course a challenge. And another thing is a heterojunction system, which is kind of electronic and optical properties of the system, where we used to do the structure properties correlation. So, and then finally the nanotechnology technology in biomedical applications and environmental remediation. This is also one of the focus. But if you see very in deep, that most of the research focus based on the surface and interface effect. So why surface and interface effect? Because whenever we are talking about nanotechnology, small materials, then surface of the materials or interface of the materials become dominate to play the role to control the properties. So this kind of system I have chosen, which can show the different property than their bulk system. And so if we make some interface coating and or make the system very thin, confined, then we can get completely novel properties of the system instead of inserting some new materials in the periodic table. Okay, and this is, as you know, inserting new materials in the periodic table is not that much easy, but with the available material we can get the different properties of the material, sometimes which may be very much useful for the particular application purpose. So that is the main goal. That's why just our group is called the Surface and Interface Science Group, Nanomaterials and Energy Research Application, where we used to do. So these are my just existing group members. Some alumni is also there, and research grants, of course, Indian research grant, DST, CSIR most importantly, and so our research also used to give the research grant from international research funding, like DAD, Germany, DAISY, Germany, and also New Mexico State University, where we used to get the funding from through the NSF. So that is the most of the focus of the group, and some elaboration of the surface and interface means what. So as I have told already, nanomaterials and confined system shows the effect, where I used to tell the surface and soft matter physics. Whenever I am talking about, mostly we used to focus on the polymers, hydrogels. Of course, again, you should remember that the confined system I am talking about. Then energy research, where we want to talk about the building better batteries. At this point, aluminum and lithium batteries I am working on, and for the materials for the application for the solar energy conversion. Next and last one, the biomedical application of nanotechnology, where we used to make the materials, as I have told, hydrogel and magnetic nanoparticles, for an example, the combination of these two, so which can help to get a better dye-absorbing material or drug delivery system materials for the drug delivery system. So such kind of potential is there. So you're working on this field. Now I'm going towards our lecture, so which is the design of novel materials for that main targeted problems is for energy research. Second one, nanoscale device in the field of flexible electronics, photonics and optics. I mean, or you can say. And third one, as I just briefly, I'm telling medical diagnostic and environmental remediation. So, which is magnetic nanoparticle, embedded hydrogel, as I have told for an example. And for this, there are many publications, some selected key publications from our group. So these are there from myself or our group members are involved there. So you can see from this, so these are very important field, and of course today I will focus on the energy research. Okay, design of novel materials for the energy research. So why energy research? Most of us are already familiar with that. So there is no limit for our requirement for the energy field in terms of energy. Okay, so this is ever increasing. So global power requirement is ever increasing. Now we need high performance advanced material technologies for alternative and sustainable energy. So that means we need, whatever we have, it is not sufficient, because every day, based on our progress in the electronics and every requirement in our lifestyle, everything, so you need more. So for that, without new materials, it is difficult to achieve that. So new materials to get the alternative and sustainable energy. So get the energy means, of course, if you are talking about fuel cell, or that means fossil fuels and like that, this is going to be finished very soon, as we know. So for that, of course, it would be really good to have the alternative energy or renewable energy or sustainable energy. We can tell in different way this same kind of information. That what does it mean? Actually, as you know, we can't generate new energy, right? Mass energy conversion is there, but otherwise energy conversion, energy to energy conversion. So in this case, the ultimate source of energy is the solar energy, and the conversion of solar energy to the two different energy, let's say electrical and photocatalysis and different chemical energy, so like that, right? So the conversion of the solar energy, the main point, because that is the main source of our energy. So, and if we can do that, so this is sufficient. So that would be fine for us to get the required energy. So for that also it is not so easy to convert that energy. So for that also we need the different materials. Of course, many people are working on the solar cells for this. To get the higher efficiency and like that. So still the efficiency is not that much great, and for many materials used to prepare for another hydrogen fuel cell and like those kind of things. So now we new materials are required, or advanced materials are required for alternative and sustainable energy. Second one, what we need, okay, we can convert the energy. As you know, solar panel, we can change the energy, convert the energy, but so that energy, how to store? Because if we cannot store it, then when the day when there will be no sun, or in the evening, how can we spend that energy? So that is difficult. So that is why storage is also very important, because the country like India, there is a huge, we can get the exposure from the sun, but the problem is that if we do that, as much as I can get from sun, the energy conversion, but we don't have that much storage system, so that we can store most of the energy without wasting everyday's energy like that way. Okay, so that is a second challenge, is to get the better electrical energy storage, because we have, of course, all of you, we know that we have in our computers, mobile phone, and everywhere we have the batteries, right? So these are the batteries, are the energy storage. Of course, capacitor are the also energy storage. So these we have already, but this is not sufficient as per our ever increasing global power requirements. Okay, so 2 points here. One is energy conversion, or renewable energy, sustainable energy. Second one is the storage of this energy. Okay, so these two challenges are there. So, and then for this energy storage, the battery, as I am saying, that it is there. It is not like that it is not available, but we need to get it better. So what are the challenge? Better means in terms of high performance, better performance, whatever be the performance, I can say in that term, that more capacity. That means it can help you to run your machine or instrument longer time, or your car longer time. Okay, and next and most important is safety, because that as I have shown just in a kind of picture from the internet I have taken only, so you can see that many laptop you can get, it is warming up, so if we just kind of that is sometimes blast and like that also occurs. So safety is a important crucial point or important challenge we have to overcome, because if you use a lithium ion battery, safety issue is always there. But lithium is a really important metal ion battery in terms of its higher energy density, so power density, and all these other perspective. Okay, so third one is the stability, lifetime, better cycling performance. Means what? That means, okay, this is rechargeability, because if I get single kind of cycle, and I can get the good performance. That is, first cycle it is a very good performance, but second cycle it is getting maybe 90% down. Okay, so that, what does it mean? That, say I am giving some examples. Silicon has a very good theoretical capacity. Okay, if I use silicon, you will see 4000 milliampere hour per gram. So this is why I am telling this number. You can compare with the commonly commercially available graphite system, that is graphite what you used to use very commonly. So this has around 370 milliamp hour per gram. So silicon, if we replace it, 4000 means you can imagine that more than 10 10 times, 12 times, like that way. Okay, so but the problem with silicon is that whenever it will first time it will give a good capacity, but after that volume expansion is so high, it will be cracked. So you will not be able to get and a rechargeability, so one time use kind of, okay, and even that is not also in between also it can be cracked, so kind of volume expansion is too high. And I am giving one example, but there are many other kind of examples where you can see that the stability will be is very poor because of the interaction with the electrolyte electrodes, so those kind of chemical stability is very bad, thermal stability is very bad. May say I am taking one battery, where that is battery means the instrument with the batteries, maybe car or maybe other things, mobile or computer, so you are going in a CHN, so where the temperature is very low, so then your performance of the battery will be completely different than the normal, because thermal effect is there. So those kind of things are there, okay. So we have to that for the kind of many different purpose, say army and other places, we need to go from the some extreme temperature and also space and all these things. So there, if you want to think about that, so we have to check that thermal stability as well. So that stability is one. Second one is a lifetime. As a lifetime means how many cycles, how many times, that many times we used to see how our laptops are charged, this cyclability is kind of after 5 years or like that, battery is not working properly, so that means it is very difficult to charge the battery again, and it will not be used like that way. So these kind of issues are there, challenges are there, we need to overcome. And the fourth one, of course, the cost. So if it is very expensive, already if you go for the electric car, so it is very expensive. So then we need to get the materials for the reduced cost as well, because if it is not cost effective, it will be difficult to use. So all these things, so you cannot expect that in a one turn all the problems will be resolved, but of course we can give a try for that. So one challenges are like that. So in this case, as I have told, two things are there. One is materials for the conversion of the solar energy, first one, and second one for the materials for the electrical energy storage. Okay, so as my lecture topic is today that the materials engineering for the energy research, so I will just I'm going to give some case studies kind of or example kind of for the materials engineering, so where you will see the effect of surface interface so dominating that then in that case how it can change the properties of a inert material completely, because of the some 1 or 2 layers of different coating. Okay, such kind, so that example will come. So that is the materials engineering. Of course it cannot go like a arbitrary way, so there will be some background why we'll use this material and why we'll use that kind of coating, or the itself that material will be confined to get the different price. So choice of the materials of course will be an first important things, and why that is what kind of coating or what kind of interface we want to utilize, that will be also based on the properties of the material, theoretical background of the materials and like that. And second one, as I have told, the materials for the electrical energy storage, the similar way that how we can enhance the properties of the electrode material by changing its surface and interface, or designing the materials. Okay, so these two. And for this, in this case, I have chosen one example for both the cases, so that it will be easy for me to tell that how kind of giving an example of epitaxial graphene on silicon carbide. So using this system, how it can be useful for both the cases. So for the energy storage, how it can be, I am not telling that will be the best system, but I wanted to focus on the how we can design the materials to change the properties of the material to achieve the our objective, that is the solar energy conversion or the energy storage system, that electrode properties of the electrode, how can we enhance. So for this I'll just first, as I have told, the epitaxial graphene on silicon carbide system. So you can understand the silicon carbide is the main bulk material, and after on top we want to put or we can want to graphitize the system. That means few layers of graphene. Okay, few layers of graphene means that the two layers, the separation between two layers of graphene is around 3.4 to 3.5 angstrom, like that. With 3.2 to 3.5 people used to report in the literature. So that kind of, so within that single or bilayers of graphene or few layers of graphene, how the properties of the full system, that means epitaxial graphene on silicon carbide, can be changed completely or enhance their inherent properties. So that will demonstrate today. So just quick things, or many of you are I think know about the graphene, because everywhere graphene is novel material, it's novel structure. So I'm just giving brief, so quickly, just to remind you. So this is a honeycomb structure, graphene honeycomb structure, and you can see that what is the importance. There are many importances because of this kind of structure and their sp2 bonded this atoms. So I'm just coming to the next slide also after that. So this kind of structure can when they will be separated little more, then they are just a graphene layer, so we can say. And of course, why I'm telling the more, because if you go for the graphite, they will be stacked more closely, and in the graphene layers they are kind of considered that very couple of layers of the graphite, you can select that kind of graphene. Okay, so then if you roll these graphene layers, it is the nano carbon tube. Okay, and then if you just make a kind of ball, so then it will be like a fullerene kind of structure. Okay, so all these things are bases are the graphene. Okay, and why I am giving this example, if you give the internet search, you will get many different properties, many applications for such kind of fullerene, carbon nanotube and graphene itself. Of course, this is the basis of the graphite as well, because the stacking is for long infinite number of layers of graphene is called the graphite only. The separation will be more closer. Okay, so just quickly, that why sp2, I was saying that why graphene will of course there are huge theory. We can just make complete lectures of 20 lectures maybe only from graphene, but I am not going to do that. I'm just giving few important properties, at least we should know to just understand these lectures also. So in that case, that sp2 hybridization, just schematically, that how it for the carbon, it is just 1s 2s, and generally for C in the graphene it used to be like that way. When it is in the excited state in the for the carbon, so 2s, that electron can go to the 2pz, and then the remaining this, it is a schematic for this, the 3sp2 hybridized structure you will get, and one which is unhybridized orbital. So these three is generally used to be considered as the planar things, and the unhybridized orbital will be the vertical. So these vertical orbital is delocalized. Okay, this delocalized kind of pi electron, that will give you the free electron kind of metallic kind of properties. That is the free electron properties. Generally other carbonaceous material you will not be able to get such kind of properties what we used to get in the graphene. Okay, so all these six delocalized kind of orbital will give you for the full graphene plane the free electron availability of the kind of free electron. I'm saying that. Okay, pi electron, delocalized pi electron. So now next, if we just go for this, as I have told, graphene on silicon carbide, epitaxial graphene on silicon carbide. Because why I am talking about epitaxial graphene, just keep in mind, so graphene we can get from that Nobel laureate in fast when graphene, so it is, you know, that Scotch tape method. So you can get the graphene layers from the graphite, okay, just separating the layers from by Scotch tape method, okay. But in case of epitaxial graphene, what does it mean? That is when we are trying to grow the graphene on silicon carbide. That means silicon carbide you have, now you are just trying to evaporating the silicon atoms, and then remaining carbon atoms will rearrange and then make the graphene layers. Okay, it is not that we are creating we are just growing graphene layers separately, maybe some chemical method or from Scotch tape method, and we are depositing on the silicon carbide. What we are doing, we are growing the graphene layers on top of silicon carbide. Okay, so here few things are important. So I have shown in the 2 dimension is the silicon carbide structure, and then so this is 6H silicon carbide structure. So separation between, that means hexagonal, okay. So this separation between this one layer to another layer is, if I just tell that D006 is around 2.54 Armstrong or like that, and then these atoms to the some one layer will be there. This is called the buffer layer. Okay, so this is not graphene, this is not silicon carbide. So in between. Okay, so this is 6 root 3 structure that used to take. So some literature used to say that okay, there is also another structure which is root 3, and then 6 root 3 forms. So there are many kind of publications, papers on that. What is the interfacial layer exactly? But many papers just claim that okay, there is a finally there is a 6 root 3 structure which is connected, one at least carbon atom is connected with the silicon, and then after that the graphene layer used to form. Okay, so that means in between graphene layers, so if here I have shown one single graphene layers, so after that what will happen, this layer will be another graphene layers, and then second silicon atom will be evaporate, and then buffer layer will be created here like that way. Okay, so few layers of graphene can be formed like that way. So this is the kind of structural information of that. Of course, when I am telling these things, this is the information what we can extract from the different characterization technique, because we can't see this kind of atoms just only by bare eye, right? So different characterization techniques can give you this information. I have given the gist of this information there. Okay, so now what is the I have told that graphene, epitaxial graphene on silicon carbide first. So now if you see that there are different, as I have told, this is the epitaxial graphene on silicon carbide. So both technique, I am going to talk about the couple of both technique for this such kind of formation. So one is like that way, if we want to grow the epitaxial graphene at kind of ultra high vacuum, so in that case around lower temperature, I'm saying 1300 degrees centigrade, you can get the graphene layers by after evaporation of the silicon atoms. And you can see that from STM images, that how all the single monolayer honeycomb structure you can see very clearly. For a good instrument and expertise, you can just get such kind of data, and many reference paper used to show that. So such kind of growth is there. So this is if you want to do for the ultra high vacuum system, if you want to grow. Now if you want to grow for the ambient pressure, okay, so ambient pressure means not the ultra high vacuum pressure. So in that case you need to go for the much higher temperature graphitization, maybe around 1700 or more, okay, degree centigrade. So for the ambient pressure we can throw the argon gas to get the ambient pressure and this thing. So we have developed here, so that this ambient pressure graphitization process. So silicon, as I have told, silicon is supposed to be evaporated and graphene layer will be formed and rearranged. Of course, here I would say there are many controversy about that, how this graphene layers form. So all agree that I mean graphene layers formed by this method, but the process, many very good journals, PL and other journals are there, so they are claiming different process to grow the graphene layers here. So they are just trying to explain the phenomena in different way, but most well established explanation is that, so that at the high temperature silicon atoms will be evaporated and these will be rearranged. So I am giving that impression here. Okay, that is the way maybe to form the graphene layers. Okay. So as I have told, we have developed this process here, but of course for the low temperature graphitization also we have used, in my previous work at my, at US University, Northeastern University. So there I have used the both the things, that is the ultra high vacuum as well as ambient condition, to see the what is the changes and what is the difference like that. To the in that case I can mention that, so actually for the ultra high vacuum graphene layers, of course it is very good quality, but the problem is that there you cannot put very bigger sample in the ultra high vacuum system. Ultra high vacuum means you can see that here around 10 to the power minus 10 torr, like that way. So here your chamber will be very small, otherwise it is very difficult to maintain that kind of pressure. So that is why you are restricted with your sample size. Many experiment doesn't matter with the smaller sample size, maybe 5 by 5 nanometer, 10 by 10 nanometer is good enough. But for many experiments or many requirement for practical use, maybe the bigger sample size is required because of large scale deposition. Okay, for the for the application purpose, ultra high vacuum system is always a kind of limitations, because you have to, it is expensive one. Second one, you have to be restricted with the smaller sample size, as I have told, like that. So in that case, for the ambient pressure, if you want to graphitize, then it would be a good process. For the high temperature graphitization around 70, as I have told, more than 1700 degrees centigrade at ambient pressure. Okay, with the inert gas, because we don't want to get the contamination from the present gases. Okay. So now, as I have told, very good, we have grown the graphene layers, but how can they say that, because it is a 3.2 Armstrong separation of the carbon layers, how can we say that okay we have grown the system? So I am not saying me, but in general, so there should be some appropriate techniques to detect such kind of smaller kind of interface coating or interface changes. So for this kind of interface study, I'm not talking about graphene only. Of course, graphene is 3.2 and 4 Armstrong. Many few layers means maybe 3-4 layers means even 10. I mean 12 nanometer. Sorry. 12 Armstrong or 1 to 2 nanometer within that, not more than that. Okay, within 1 nanometer you can say. So this is very thin. So it is not so easy to see bare eye, as we all of us know. And the similar thing is for the any other coating. If I am talking about, whenever I am talking about materials engineering with the surface coating, with the interface effect, such kind of words, then I need to find out what is the technique, how come I can just resolve such a smaller dimension. So in that case, X-ray reflectivity is a very good technique, very useful technique to just detect such kind of small thickness. Okay, so Armstrong order resolution kind of thing. So I have given some kind of just brief, as all of you know, this is a short-term course, but if I want to teach the X-ray reflectivity technique, so it will just kind of many books like that way. So but the gist I am trying to give, so that if anybody is interested, they can go and check in the books and like that. So at least they can get a glimpse that what we can do and how, what is the idea about that. Okay, so in that case, as I am showing that if you say the substrate, silicon substrate is there, just like for an example, I'm not talking about silicon carbide, if it is silicon carbide even. So this is the X-ray reflectivity is always a low angle X scattering. Why am I saying low angle X scattering? Because many of us are familiar with the X-ray diffraction, or most of the cases for X-ray diffraction we have to go for the higher angle. Higher angle means I am talking about more than 10 degree. Mostly we used to start from 20 degree 2 theta angle. Okay, but for X-ray reflectivity we need to get our whole data will be finished within 8 degrees or like that with 2 theta. Okay, so why? Because here we used to do the very grazing incidence reflect, kind of, principle is like diffraction only, but we have to go from the smaller angle to little bigger angle. That means from starting from the 0 millidegree to around 8 millidegree, and like that. If it is a smooth film, that interface is smooth and surface is smooth, we will get with the film thickness that kind of fringes. Okay, so as you can see that, as I have shown schematically, substrate and then film and then air, and then you can get. Of course, just keep in mind the film thickness, if it is kind of more than 120 nanometer or so, that means 1200 Armstrong, then maybe I'm saying that number, not exactly 1200. I'm saying that if it is the higher thickness around 1000 Armstrong or 10 more than 100 nanometer or so, it is not so easy to see the fringes, because you why? As you can see that it is kind of plot 2 theta. As I have told, 2 theta will change. The 2 theta is in the, now if we convert it in the reciprocal space momentum vector, so 4 pi by lambda sine theta is equal to qz. So in this case, if you see that the separation between two deep is equal to, inversely proportional to the film thickness. So if film thickness is much higher, then this separation will be very lower, so it will be very congested, and we will not be able to resolve the deep point. So we get our estimation will be erroneous. But if it is below that, the technique will be great. But of course, as you have understood that if these fringes are getting very close, that will be a problem. And on the other hand, if the fringes become very broad, that is maybe when the film thickness is 1 to 2 Armstrong, so that will be again difficult, because the separation of these deeps will be too wide. Then your background will come, because you are taking the data, and after 8 degrees and like that in a low angle, your background will come and you will not get the real deep. So you cannot estimate that, because at least 2 deeps are required to get the film thickness. So very low is also a problem and very high is also the problem. But within, I'm saying that kind of 1 nanometer to 100 nanometer, that is the very good technique to get the, I'm saying 1 nanometer means I'm saying even for 5 Armstrong, 0.5 nanometer to this, it will be a very good technique to get your film thickness from this technique. Of course, just keep in mind these fringes and these things will be deteriorated if your surface is very rough or interface is very rough, because the theory behind that, how we have got the technique and how you can analyze the data, because here I have shown just schematically for your understanding, quick understanding, to get the concept how it is inversely proportional and directly proportional, that I have told that okay, del qz is equal to 2 pi by d, that is separation between 2 divs are inversely proportional to the film thickness. But when we gave the real values of the films, interface roughness, surface roughness, all these things, then we have to feed the data with the theoretical model. This theoretical model is based on the complete X-ray mechanics, and also that layer structure and how that X-ray optics will work based on that transmission, and just considering the anomalous dispersion of the X-ray wavelength, and all considering the interface roughness, how it will contribute. So these things are incorporated in the analysis. So the model, with the model will feed the data that will give you all the information there. Okay, so so this is a very important and in-depth knowledge you need to extract the real numbers from the fitting the data. Okay, so this is the, as I have shown schematically here, so it is the incident angle and it is the reflected angle. Okay, and X-ray, as you know, and maybe in the next day I have lecture, so I may go for elaborately for these techniques also for that time. Okay, so here mainly important thing is that so you are familiar with the optical wavelength. There you can see the optical wavelength when internal total internal reflection, we are familiar with that. But for X-ray, what happened, total external reflection, because X-ray behaves differently than the optical wavelength, although both are electromagnetic wave, we know, because of the refractive index of the materials, the real part of the reflective index of the material, the delta term plays an important role, because this delta term based on the X-ray wavelength, that will give you a less than 1 value for the refractive index. So that maybe I will explain in the next day, if I just go for these details of the X-ray technique that day. Okay, but this is the main thing. Based on that, if you understand the X-ray scattering theory, is established based on that, because that is why this X-ray reflectivity, when we are doing very low angle, then it is just because, as you know, for the optical wavelength above the critical angle, then total internal reflection will come when the light is going from the denser medium to lighter medium. Okay, for the X-ray, when light is, that means photons, X-ray photons are coming from the lighter medium to denser medium, that means air to the material, then it will be, so there, if the angle is so for the critical angle, that will be completely below the critical angle, that will completely externally reflected. So it is called total external reflection. So just if we go a little bit more than the critical angle, then it will start penetrating into the system. Okay, so as I have shown here, so this flat region, if you see that one, that is reflectivity, it is that from the, it is below that, this corner where when the light has started to enter to the system, then intensity will, reflection will be getting reduced. But before that, it will be continuous one kind of, ideally. Okay, because this is the total external reflection. So maybe it is new thing, new point, when you are dealing with the electromagnetic wave within a range of X-ray. But when you are working with the optical wavelength, you will never get the external, total external reflection, total internal reflection, as we have learned from the our junior grade and like that way, right? So that is the main essence of developing this X-ray reflectivity technique or any other grazing incidence technique for X-ray system. Okay, so and this technique is not only the X-ray reflectivity, as I have shown, that GID, grazing incidence diffraction, grazing incidence small angle scattering. These techniques are very important to explore the features, in plane and out of plane features of the nanostructures. Okay, and if you change the interface, then how it will be changed, because it is non-destructive method. X-ray scattering is mostly, if we don't use the very intense beam, okay, so then the mostly it is the non-destructive method. You can get the information by kind of sputtering through these things, kind of, I mean, FIB, focused iron beam etching, and then you can get the information also. But in that case, your system will be damaged. Okay, so of course, there is, every technique has some advantage and disadvantage. So in this case, that is why X-ray technique, and you need the very good specialization for to analyze the data. But the technique is very good for the system without damaging the system. You can just probe the not only the film, also the interface, that means buried interface also. You can get very clearly what you cannot see in the, exposed in the system, but X-ray can see, because X-ray can go through that and give you the complete information how the nanoparticles are sitting. If something is, structures are going on at the interface, that information you can get from these techniques with proper analysis, then without damaging the system. Okay, so that is the essence of this technique. So I as I have told, I have shown just a glimpse of these things, but very details are there. So here, basically, I have shown why the silicon carbide structure, if you consider the kind of stacking atomic layers and like that, how in the reciprocal space the momentum transfer and like that. So some images from our experiments at the synchrotron at APS, that is Argonne National Lab. This is because there you can see that we can use such kind of system when we are doing the battery research directly in situ experiment, how it is changing. We can see that we can put the electrolyte inside the system, we can extract that, all these things we can do during the experiment. So, and we can change the voltage of the systems. And why I am talking about the synchrotron? So because we have at our lab on many institutes, we have the XRD machines, but lab source intensity is not that high to penetrate within the such kind of in situ system. I am saying that why? Because there will be liquid and other covering, otherwise you cannot perform the experiment. So that intensity is not sufficient with the lab source. Then we need to go for the synchrotron source, and this intensity is much higher, and parallel beam focusing is very good, and also we can tune the wavelength of the incident X-ray beam. What does it mean? Because when we are using this X-ray beam here, source, okay, and your detector you can see here, okay. So when we are, and here we are putting the sample, and here the chamber, and like that you can just rotate everything you can do, okay. And cryostat you can use to cool down the instrument system as well. But anyways, so when we are using the source, so beam is coming like for the lab source. If we have the copper anode, we can get copper K alpha, that is around 1.54 Armstrong, okay. On the other hand, but if I have molybdenum source, so I can get around 0.6 Armstrong wavelength. But if we have that synchrotron source, so then within a range I can tune. Maybe I can go for the say 1.8 Armstrong, 2 Armstrong wavelength even. On the other hand, here also I can go for the 1 Armstrong wavelength. Like that I can change the tune the energy of the wavelength, because sometimes it is very important because of the system. If we change the energy, then we can go for the higher momentum space without, that means reciprocal space, without changing the without damaging reaching the background, okay. So that kind of, for system basis, we need to choose the which beamline we will use and which wavelength range we want to use, okay. So here because if you can remember that I was talking about graphene on silicon carbide, I am going towards that direction, okay. So as I have told in X-ray reflectivity, now I wanted to say that, okay, when, as I have mentioned, that if it is very low, that means 1, 2, 3 Armstrong, this is very difficult for initial, that means low angle X-ray reflectivity to get the layer thickness. So when I am talking about single layer graphene or bilayer graphene, they are really the thickness of the film is very low, maybe 3 Armstrong total. So one single layer means 3.4 Armstrong, and like that way. So to get a very clear feature, there is this technique. It is called that crystal truncation rod technique. Okay, so technique means uh, again measurement technique is not so difficult, but analysis technique is based on such kind of crystal truncation rod. So it looks like that, say, silicon carbide structure is there in the real space, and in reciprocal space, in Q space, you can get the crystal rod, it is called, and at the end when it has been graphitized, so it is like a crystal has been truncated. So then what kind of features we can get? So theoretically, people had, I think, a very famous paper around, I think, 90s. They were, PRB. So it was developed, the theory was developed in crystal truncation rod, and then people have started to make the programming for to get a good programming, and now there is a established programming, and many groups are using that kind of analysis technique. As I have told, taking the data is not a problem. Then again, theta to theta, similar kind of X diffraction data taking measurement, but the analysis. So getting data, how you can extract the features of the system, how can you tell what is the thickness? So if you have proper modeling, then you can feed the data with understanding, and then you can get the proper values of the or proper information about the system. So I have shown here schematically for this kind of crystal truncation rod, and I wanted to say that when silicon carbide is itself there, we can say it is an infinite crystal, but when we have just graphitized one end, so it is the kind of truncation. That's why this name came, and that rods, how we can analyze based on that, the fitting model has been developed. So here I wanted to show one example of how we can get the for the silicon carbide features as well as the graphitized silicon carbide. So here epitaxial graphene on silicon carbide, I have given the name EG/SiC. Okay, so here this two peak is, as I have told, it is a silicon hexagonal 006 plane because it is epitaxial around this direction. Okay, so 006, and the second order peak is 0012, is at 0012, and now you are just getting this hump when there is a only single layer graphene. Can you imagine? Okay, so this hump is coming, so any other technique is very difficult. Of course, if you can see from the STM, and like that initially I have shown the images, but STM is very expensive, and also you need the real expertise for that, and you can tell about, okay, within STM works for a small region. If you see the length scale, it is very small, some kind of nanometer length scale. Okay, but local image you can get, but when you are estimating from X-ray, so at least you can say that more than 2 millimeter or 1 millimeter kind of spot size you can get easily. So this will give you the overall picture of the nature of the cell system. Okay, so that way for the single layer of I am telling you single layer of graphene because I know we feed the data and like that way. So this hump you can feed, as I have told, crystal truncation rod theory model. So that we used to use to feed it, and from feeding the I'll show maybe afterwards for other things. So then feeding these things, we can get complete feature of, okay, where is the silicon atom, where is the carbon atoms, even separation be 0.6 Armstrong, 0.9 Armstrong kind of resolution we can get from this technique. So it is really good technique for such kind of system. Of course, everything, whenever we are talking about good or bad, where we are implementing this based on that. It is not good technique if I tell that means it is good for everything. Okay, for this such kind of system where I am telling that epitaxial growth for few layers of things, any other system, it can get a very nice results. If you know the analysis technique, you can get the layers very clearly, and you can just you can claim the information that okay, there is a this silicon carbide and peaks, and this on top of that one layer, and this peak will be, this hump will be sharper. Or if you take the graphite, that means many layers of graphene on silicon carbide, you will see this peak will be very sharp. Okay, so the how broad it is, based on that it is, I am saying qualitatively, I am telling, if you feed properly, then you can get the quantitatively how many layers are there. Okay, so as I have told that this is the here just for an example, we feed this and you can just see that the circles of the experimental data points, and this green color is the kind of silicon carbide model, okay, and then total convolution of this is the graphene model. So convolution of graphene and silicon carbide, you can get the total peak feet, okay, overall peak feet. So different medium, so even we can see that the separation as well as the coverage of the graphene. So maybe ideally we are thinking okay, it is this completely 100% coverage of the graphene on silicon carbide, but what we can see, the first layer of graphene coverage is 90% for this for a given system, say. Okay, second layer of graphene coverage for the parameter of growth. I am saying that of course if we know the information, we can change the growth parameter to get it, if we want to, if we can tune the growth parameters to get it where what we want. That means if we want okay, second layer should be also 90%, so then we'll just try to make it in that manner. The growth parameter, we have to of course calibrate these things with taking the many data like that. But my point is that so you can see this is the silicon carbon, you can see the carbon silicon, so it is around 0.5 angstrom I think separation. Okay, so that kind of resolution you can get. Why? Because you can see that your QZ is above 5 or 6, so the resolution used to be around inverse of that pi by QZ, like that way. So then you can get the such kind of resolution, and then 3.3 angstrom, and as I have told, graphene coverage. So we have shown the extraction. So there is a possibility that is the very good technique to extract that information. I have given this information because you will understand that okay, we are talking about graphitize and these things. If we cannot estimate, if we cannot know about that what is there, I can grow looking at the recipe. That doesn't mean that I am successful. Okay, I have to establish that whatever we have formed, it is giving exactly these things. Okay, so for this we have to check that, and if we don't know that what we are doing, that means if we don't have the idea what is, so we have to follow only one recipe. We cannot tune as per our requirement, right? We are not only reproducing somebody's measurement or analysis, so we have to go forward with our own. So another technique I am telling, because these two techniques, of course you can understand many techniques are there for many purpose. I am telling about two techniques here which are very important. So one, as I have told, this crystal truncation method for the X-ray reflectivity method for the thickness measurement of the graphene layer of silicon, epitaxial graphene layer silicon carbide. Another one is the Raman scattering, which is very important to just say that okay, graphene is there or not. Okay, so qualitatively, and after that of course from the more detailed analysis from FWHM you can tell something about the number of layers as well. But that is not very much convincing, but people used to mention in some paper that okay, that is, if it is broader then it is thicker layer, like that way. Okay, in this case, at least for the Raman scattering I'm talking about. So this Raman scattering used to use to identify whether graphene has been, so generally whenever we are working with the graphene, it is very conventional method that okay, after forming this we'll check with the Raman whether graphene has been formed or not. Okay, and quality of the graphene. Quality of the graphene means whether the coverage is good or bad. So how can you get that? So there are three kind of very characteristic peaks are there. G, which is which G peak is generally used to be, of course, again, for that also details things are there. I am just telling you the main points because I will use these numbers that, that nomenclatures in the analysis. So that's what. So G is the, for the peak corresponding to the carbonious material. D is the, sorry, 2D peak, which is mostly graphene peak actually, though how the layers are, kind of continuous and how the quality of the graphenes on its system. So this is a 2D peak around, generally if we use that 514 nanometer lasers and like that. Why I'm telling the lasers? Because for the Raman peak, if we change the lasers, of course peak position will little bit shift. So around 2700 centimeter inverse. So this 2D peak comes, and G peaks come around 1530 or something like 1514 or something like that centimeter inverse, and then D peak is there, which is the disorder peak. Okay. So this peak is that if your system is not very much ordered, then this peak will be strong. Okay, so this is coming around 1300 or something like that. Okay. And from some paper only you can see, so it is carbonious material always 1500 around, sorry, G peak will be there close, but D peak and other peaks will be how it will be changed. So they have shown from the Raman data for different carbonious material, graphene, graphite, carbon nanotube, diamond, which is again carbon 6, it is fullerene. So this how your 2D peak and other, the D peak, and it will be changed. So then that is the kind of fingerprint kind of test. So you can, looking at the data, you can tell, okay, this is graphene, signature of graphene, or no, it is just kind of carbonation material, something like that. Okay, and that has been verified also from the theoretical model. So this is a reference paper, they have shown that. So this is a important technique to get that. So we will generally, for the graphene identification, we of course will focus on the 2D peak, and G peak, of course, G is the quantity of the carbon, how much carbon is there, like that way. Okay, quantitatively you can say. So now, these are the basis of the Raman. I'm not going at this point here. So, but maybe if we talk about the techniques the next day, so we'll discuss. So now we are coming to the point. So using these techniques, I just wanted to, so first I have told you the growth of the graphene, epitaxial graphene on silicon carbide. So first point I have told that, okay, to convert the solar energy. So many examples are there to convert the solar energy, as I have told that you can use it for the electrical energy to check that after conversion, so which is the solar cell application, like that. So one of the example also the photocatalysis, so where you can get the solar energy and or you can make it available to do the catalysis process. Okay, so that is the one way. So I am going to that example. Okay, just give me a moment, I just want to have water. So then what I am saying that then say if I have told the photocatalysis. Okay, so in this case what it will be there? So electron hole first I just wanted to briefly tell about that what is photocatalysis. So first I have told it is our objective is to conversion of the our ultimate energy source, that is the solar energy, to for some use. So in this case I am talking about the photocatalysis. So it is kind of basis of this, that first we need to get the electron hole pairs. So if you make a just wavelength of light, if it is coming, photons are coming through the system which is more than that valence band and conduction band. So of course that energy, accepting that wavelength, it will go from the valence band to conduction band. Electron will go, it is supposed to be, right? So, and that is the electron hole pair formation, right? Conduction band and valence band. But the problem is that if this charge carrier migrate to the surface of the, because whenever I am talking about conduction band and valence band, a reasonable amount, so that reasonable gap I am talking about. So this is not insulator, of course semiconductor, okay? So then it will migrate to the surface of the semiconductor to contribute a series of specific reaction to perform the photocatalytic activity. What does mean that these electrons, if I can get it separated and whole can get it separated, so separated means it will not, recombination will not be there. We want that there will be no recombination, because it will be excited, and then if it is come back, then it is done, right? So there is no active electron, no active hole. So we want more active electron and active hole. So we want what? That electron will flow. That means whenever it will be excited, it will go to the conduction band, some way it will get a path to migrate, okay? And so that we can at least reduce the recombination effect. So in that case, so if we get such kind of active electron and active hole, then not only the photocatalysis, many things can be done. I'm just giving that, as I have told, solar voltaic. So I mean, basically, very crudely, if I tell, this electron hole pair is the main key ingredient to get such kind of solar energy conversion. Okay, so then it can be used for the solar voltaic or pollutant degradation, because if active things are there, electrons and holes, it can kind of activated charge particle, and it can destroy the pollutant also. On the other hand, it can do the photocatalysis as well. Hydrogen production, this active electron can do work for the hydrogen production from water splitting. So again via solar energy conversion. Okay, so key ingredient is electron hole pair, so that it can be used for solar voltaic, pollutant degradation, hydrogen production. So photocatalysis like that way. So but this is the important requirement. But always everything is not ideal, so there are many issues. Main issues is recombination. So recombination, that means whenever it will go, then it again come back, and then it will be, so then efficiency will be much lesser. What as it may not reach our expectation. So this we need to do what, that we need to make it well separated. Okay, so for that, what is the main people used to do? Use the co-catalyst. What? So use some kind of another material. Okay, so which will, that co-catalyst will do, you understand the name implied that what is the activity. So instead of, it will try to reduce the recombination effect. So for that, it will create many abundant reaction sites on the surface. Okay, I am talking, so I am going to the specific point, photocatalysis, say. Okay, so it will make the co-catalyst can make the abundant reaction site, so that materials, in presence of the materials, so whenever the material will come, say polluted material, any other, you can use the chemical dye also to check the proper efficiency. So it will, if you have many sites, so it will destroy, probability will be higher. Second, increasing the interfacial charge transfer. What does it mean? That means if you engineer that means your materials engineering is perfect, then what it will happen, that the electron hole will be well separated through this interfacial medium, that means coating. That means you are trying to use a co-catalyst at interfacial material, so through this it will transfer quickly. Okay, so that the recombination, you can reduce the recombination probability. Okay, so this for this thing, so you need to do that, enable them to absorb the more abundant visible light by reducing the band gap below 2 EV. Okay, so if you want to use it for the solar energy conversion, as I have told, why? Because 43% about, you know that in the solar UV, most of the semiconductors goes around your UV range, right? 3 EV and like that, 3.4 zinc oxide, 3.4 EV, titanium oxide little more, huh? So like that way. But that is why we need a material which will have the band gap, effective band gap will be less than 2 eV. Why? Because during that energy range, most of the solar energy wavelength spectrum, if you see, so visible range is 43%. Only 7% I think UV range, and remaining part is the IR. So it is very difficult to get the material with the IR band gap range, but visible is feasible. So in that case, that is one of the objective. Okay, so then if two objectives are there, so effective, that means with using the co-catalyst we can use the effective band gap like that way around 2 ev, or at least reducing the band gap from 3 ev to less than that. And second one, that to make it kind of metal. That is why if you see that platinum and some expensive metal are very commonly used to use for this kind of core catalyst, because whenever electron will go to the excited state, if it can get some metallic thing, so it can transfer through that and it can avoid the recombination. Okay, so in this case, that is why I have told you now, I have chosen the example for these things of the graphene silicon carbide, because silicon carbide has band gap around 2.5 eV or like that way. Okay, even of course I am not telling exactly 2.5 eV, because it depends on the polytype of silicon carbide. Silicon carbide has different kind of polytype, hexagonal, cubic, like that, so rhombohedral. So in that case, based on the polytype, its band gap changes a lot. But around, if you take the 6A silicon carbide, around 3 eV kind of, so it is not too far from the visible band gap, but it is the best if we can get close to 2, of course, but 2 is the objective ideal requirement. But if we can reduce or close to 2 eV, that will be also helpful. So in our case, graphene is the co-catalyst. Graphene is not metal, and it is not that much expensive as well. Okay, but it can be used as a co-catalyst. So because why we have chosen, because energy level of these two are matching to, that means graphene can work as co-catalyst so that it can transfer the excited electron from silicon carbide. There is a possibility, because energy diagram, I'll show the energy diagram upcoming slides. So, and after that, what we did, that what kind of, not only graphene I have just developed and it has been, so what kind of quality of graphene helps to make it better for the photocatalysis. That is the objective there. So as I have told beforehand, that Raman is the very conventional technique to identify the quality of the graphene. So it has been employed here when we grow the graphene on silicon carbide, epitaxial graphene on silicon carbide by high temperature graphitization at ambient pressure. As I have told, two type of graphitization process I have mentioned initially, right? So this is the high temperature graphitization we have utilized, and then you can see there that this is the as received silicon carbide. Okay, so we have chosen two different kind of polytype. One is 6H silicon carbide, one is 3C silicon carbide. So particle size is also different, to see that whether really it is interface effect or itself particle size is playing role, or crystal structure is playing role, because many parameters are there now. So we have to exclude that. So that is why we have shown this. We have tried for two polytypes. On the other hand, two different size range. If you see 6H silicon carbide is micrometer range, and it is nanometer range, 3C SiC. So completely in the different range of particle size, because as I have told, particle size itself change if it is reduced or increased, then properties may change. Reduced and increased means not if you do millimeter to micrometer, that may not matters, but when you are going to a nanometer size, there will be a confinement effect, so that is why we have to exclude that part as well. So in that case, so first set we have seen, you can see very clearly that one set of data, second set of data, third set of data, and how we have quantified this data set, that I to D by Ig. As I have told, the 2D is the peak and G is the another peak. So 2D, if we take the ratio of 2D versus G, Ig, so we can quantify about the quality of the graphene, because as I have told, 2D peak is representing the nature or the quality of the graphene layers and interface, of course interface layers as well. On the other hand, G is the quantity of the carbons. Okay, any carbonous material can show G peak. So if we take the ratio, so how it is getting better with respect to the available carbon atoms, so that will give you the quantification. So that you can see, so I to D by Ig 0.3, 0.8, 1.0, so it is getting better here, and that way we have tried to name the sample by I to D by Ig. That means it is the parameter. Okay, so how the quality of the graphene is getting better, and in that way how the photocatalysis, a photocatalytic effect can be better, worse, or whatever it is. Let's see. So then of course Raman, as I have told, qualitatively you can see, and since in this case we have chosen the particles kind of, okay, so all the particles are there, as I have told, so 17 nanometer, 14 micron, like that way. So here you can see the particles. Okay, this kind of particles we have taken. So for X-ray reflectivity would not work in that, so because for X-ray reflectivity you need the proper substrate kind of interface. Okay, so in this case, so we have to see Raman is a good technique, and another one is a for local information, as I have told, for the TEM microscopy kind of thing, or STM, those kind of things, you can get the local information. So but you can see that, okay, this is consistent with the HRTM. So you can see the separation between the graphene layers and here silicon carbide, clear feature of that. So when we are getting the better 1.5 I to D by Ig, so you can see the graphene ribbons kind, I mean it is forming on the surface, and when it is kind of I to D of 0.8, so you can see the graphene layers, but not the numbers of graphene layers, as well as the quality of the graphene layers are different in these two cases, because interface here much more sharp interface here, it is a kind of hazy interface as well. So that quality is locally we can check from TEM also to see the consistency with the graphene layer Raman data. So now, as I have shown, the XRD patterns and everything can show the particle size and crystal structure, as we are bought the silicon carbide, but we have to confirm that whether the phase of the silicon carbide or not. What is this? And now the photocatalytic activity. Now, if we do that, the photocatalytic activity with I to D by Ig 1.1, that is higher. So that you can see it is. Now first I am showing the SiC, that is the additive silicon carbide. So this has the band gap, of course reasonable to get the UV light from the solar spectrum, and here we have used the exact UV lamp to use the band gap, and you can see that we have used the dye, methylene blue dye, which have the peak around this 540 nanometer. Okay, so but this dye have been used to probe that photocatalysis activity of the SiC silicon carbide. Silicon carbide, additive silicon carbide means where there is no interface effect or graphitization. So that you can see that after 240 minutes even, so of course silicon carbide has photocatalytic activity as I have told earlier, because that's why we have chosen. But after 240 minutes even, it is still there. Methylene blue has not been destroyed completely, dissociated completely. But if you see that when we are just graphitized silicon carbide, you are using here, of course, as a good quality I2D by IG is 1.1, then you can see in 105 minutes it is completely disappeared. So this maroon color line. So in 90 minutes it was something, some amount was there, and after that within next the 30 minutes, next 10 minutes, 15 minutes, it's just disappeared. Okay, so then you can see that the properties has been improved so much in presence of the graphene layers. Okay, just only couple of layers of graphene, 2-3 Armstrong, sorry, 2-3 layers, 1 nanometer kind of. Okay, so now if you can, so for a different I2D by IG, if we plot, so we can see the K is the parameter which can tell about the, that is quantitatively tell about the how the photocatalytic reaction has been enhanced. Okay, and so then if you are seeing that K is increasing when your I2D by IG is increasing, but the in a really nice manner. So and then we have plot the C by C0 also, how it is changing, and now you can just see that this is in the log scale. Okay, so if you impose that graphitized silicon carbide and compare with that the normal silicon carbide, so few layers of good quality graphitized silicon carbide can enhance 1000% performance of the photocatalytic activity. So you can see that this is more than 0.1 and as received was less than 0.01. Okay, so if you just divide and like that, you can get is around that percentage. Okay, so that can say that how few layers of graphene is helping to separate out that electron and hole and make it more active to get the photocatalytic activity much better and making it suitable for to absorb the solar energy. So that I will show in the next slide. So this is the slide. Okay, so here what I was saying that, okay, I have told you now first that, okay, we want to get the system wavelength also, I mean wavelength or energy also around 2 eV. So if you see that when the black one is the I2D by 0, so that means as received silicon carbide. Okay, so after that with the graphene I have shown some examples. The blue one, if you see that it has been shifted a lot. Okay, so band gap, if I plot, it was 3 eV as received silicon carbide, but when we have got the good I2D by IG, that means good graphene layers, good quality of graphene layers, you can see it is getting around 1.6 eV. So it is less than 2 eV, and it is really good reduction in presence of the graphene, few layers of graphene only. So this is the materials engineering, I'm saying the example. So how you can just changing the, just only engineering the same material, you are not using, you are not inserting new materials in the periodic tables. Okay, new elements in the periodic table. So available materials you have, and you are trying to carefully technical engineering so that you can get a better performance out of it. Okay, so graphitized silicon carbide, you are getting 1.6 eV band gap. On the other, when normal silicon, same normal silicon carbide without graphitization, it is around 3 eV, and you can tune. So maybe at some point your requirement is not 1.6 eV at some point, so you can tune if you know the technique, if you know the engineering technologies and what I have to do for the materials. Okay, so and not only that, another thing is very important. If you see the absorption of this graphitized silicon carbide, the graphene absorbs a lot. Okay, so for the full coverage graphene, or high quality good full coverage, I would say, because there should be required some kind of holes for silicon carbide to interact with the dyes also. So but anyways, so better quality graphene is giving you the higher absorbance is lower, it is lower, higher wavelength means lower energy range also. So it is giving, you can see that much better absorbance. So solar spectrum where the 40% of 47% of the light is in the visible spectrum, so you know that this range is 450 to 750 or 800 is completely in the visible range. So it absorbing property is getting much higher in that range. Of course peak is also shifting, the band gap is getting reduced, and not only that, normal thing also, red one also you can see it is getting higher, and in blue it is getting kind of much higher the absorption with respect to black. You can see the visible range. So it can get more energy, more spectrum, that means from the solar spectrum more it can absorb more wavelength range or energy range from the solar spectrum. So these two are very important, you can understand that. Okay, so band gap reduction, so and intense broad background absorption in the visible range, okay, with increasing I to D by Ig. So that shows that, and also as we have seen already, the enhanced photocatalytic activity. Actually these are the reason to give you the enhanced photocatalytic activity as well, okay, or both are simultaneous. Okay, so we can say that graphitized silicon carbide has potential to get the to make the efficient solar energy conversion application, to use it in the efficient solar energy conversion application. Okay, so here I can tell you the mechanism of this. Okay, so here the mechanism is that as I have told that we have not selected the material arbitrarily. Of course we have to check where is the Fermi level of the graphene, whether it would be able to transfer the electron from the conduction of silicon carbide, because it is schematic representation, but you can get the values from here. So it will be coming, it is conduction band lies higher than this Fermi energy for the silicon carbide and then graphene, and then it can, then this can give you the possibility to interact with the dye available in the solution to react with that. So reaction for with the rhodamine dye and this oxygen things, because that rhodamine dye we have used for just kind of example dye to check the photocatalytic activity, which is very commonly people use to check that. But the system we have chosen not only for rhodamine dye, so that energy level needs to attain that energy which will be useful to evolve the hydrogen evolution, or that means potential to have the to create the hydrogen evolution, as well as to get it for the photovoltaic application. Okay, so otherwise, because if I use some other this energy level where we are, so that is very important. Okay, so here I have told some the how it work, that for the oxygen reduction and kind of rhodamine dye reduction for the holes and electrons, both are separated now. I mean many are separated, much amount of electrons are and holes are separated, and they are active, creating, or they are active to for the dissociation of the rhodamine dye. Okay, dye reduction. Okay, so that is the thing, and if you just want to see more detail, you can check this paper, Advanced Material Interface. This is a reference. So that is the gist. So how we can make the epitaxial graphene system, tunable structure and properties for the photocatalysis here I have shown, but also from the properties of the band gap narrowing as well as visible range absorption, enhancement of the absorption in the visible range. So that those and photo enhancement in the photocatalytic activity, 1000% enhancement. So these 3 points are very important and made this system potential for the potential application in the for the hydrogen evaluation process and water splitting, and of course environmental remediation. Because why I'm saying environmental remediation, dye dissociation or dye adsorption is related to the environmental remediation as well, because polluted in the water you can just dissociate with this kind of material as well. Okay, so next, I will talk about as I have told, I have chosen the same example how graphitization helps to that means materials engineering or design growth, I can say. And because of design growth or materials engineering, the surface and interface effects, how it will be useful for the energy storage. For this example, I will choose also. I will demonstrate also for the similar system, that is a epitaxial graphene silicon carbide. So, but before that, before going to this system, that means for the system for this electrical energy storage, which is lithium ion battery, I will discuss about the electrodes for the lithium ion battery. Before that, I just would be happy to if you have any questions till now whatever I have taught. So it would be better to discuss that point first. Okay, then I may go for the next. Hello.
Yes, we are here. We are here.
Yeah.